I'm Professor Bennett Maruka from the University of Delaware's Department of Physics and Astronomy, and welcome to the Fall 2019 Harcourt Ace Vernon Memorial Lecture, which is generously sponsored by the Mount Cuba Astronomical Observatory and the Mount Cuba Foundation. The observatory hosts a variety of public events in addition to this lecture series at their location in Greenville, Delaware. If you'd like more information about their public nights and family nights, please check out their website, mountcuba.org. Tonight, I have the honor and pleasure of introducing our speaker, my colleague and friend, Dr. Kelly Couric. A Michigan native, Kelly completed both her undergraduate and graduate education at the University of Michigan. After earning her PhD in space and planetary physics, she joined the Smithsonian Astrophysical Observatory, where she continues to serve as an astrophysicist specializing in solar physics. Drawing on her scientific expertise, technical proficiency, and management skills, Kelly has made critical contributions to multiple flight missions. Soon after arriving at the Smithsonian, she held leadership roles on NASA's TRACE spacecraft and the XRT instrument on the Hinode spacecraft. Later, Kelly served as project scientist and project manager for NASA's record-setting High-C rocket mission. Kelly currently serves as the head of science operations and the deputy project manager for the SWEAP instrument suite on NASA's Parker Solar Probe. Launched just last year, PSP has already passed closer to the Sun than any prior spacecraft. Over the next 6 years, PSP's orbit will draw it still closer to the Sun and is expected to pass through the Sun's atmosphere, the solar corona. The SWEAP instruments directly sample the plasma flowing out of the Sun, the solar wind. Data from PSP's first 2 orbits were publicly released just yesterday, and tonight, Kelly offers us a glimpse of PSP's first scientific results, which will be formally announced over the coming weeks. In addition to leading cutting-edge research, Kelly remains committed to science education and diversity in the scientific community. She founded the Smithsonian Solar Physics REU internship program, as well as the Space on the Hill education series for Congress members and their staffers. I can personally attest to Kelly's skills as an educator, as I had the very good fortune of getting to know her when I was a young graduate student. Her scientific expertise and wise counsel, along with, on occasion, her excellent taste in wine, helped me to survive graduate school and to become the scientist I am today. So now, please join me in welcoming Dr. Kelly Couric.
Thank you, Ben. Thank you, Ben, for that warm welcome. I'm so happy to be here tonight sharing with you something that was 10 years in the making of my life and over 60 years in the making of the US and in NASA's life. The NASA Parker Solar Probe, touching the Sun's atmosphere, a tale of the extreme spacecraft that we had to build in order to try to touch the Sun, and the solar storms that we're trying to really understand, and why it's a really practical matter as well as a fun and intellectually stimulating matter. So this is me, and this is the High-C rocket that Ben mentioned. And so I started off my career many years ago, it now seems, as a rocket scientist. And so I studied the Sun through imagery. And as well as imagery in Parker Solar Probe, we have these what I'll call squiggly line plots. They're actually plasma detectors. So they're going to tell you things like temperature, velocity, and direction of the gas or the hot plasma that we have out in space. So I've done a little bit of both. I've both taken the pictures and we'll talk about these squiggly lines. I work for the Smithsonian, which sounds probably odd because you've probably heard about our museums on the mall, but you didn't realize that we also have research centers. And so although the Natural History Museum is lovely and I would love a pair of these shoes, the Smithsonian also does things like telescope. That's the High-C telescope before it was actually launched. That's the insides of the telescopes being tested. And I would also like a cuddly panda panda. But working for the Smithsonian doesn't get you a panda automatically. But what I am here to talk to you today about is the sun. So if you look outside in the sun on a day like today, you might make a glimpse of this. And this is what most humans experience during their lifetime when you talk about the sun. Now, also, I have to warn you, don't ever look directly at the sun with your unsheltered eyes. That will cause permanent eye damage. So if there is an eclipse or something, you do need glasses beforehand, but there are safe ways to look at it. But this is the normal way that you would see the sun. And throughout the ages, this is a 1571 painting of an eclipse, of the sun being eclipsed by the moon. The moon goes in between the earth and the sun, causing shadows, causing darkness to fall on the land. Animals come in to roost. Animals think it's nighttime. It gets colder. I just experienced an eclipse this year in Chile, and we had one in 2017 that passed through the United States. And in 2024, we'll get another chance to have a great American eclipse that you'll be able to see totality. And this is one of the things that astronomers have studied, and was able to actually study the sun and see it not just as the vision of these yellow rays of light, but to actually see other things streaming off of it. And so this was kind of one of the first ways that we knew that the sun wasn't just a ball, just this ball of gas, that it seemed like there was something else there, something that was actually interacting and moving away from the sun. And in the eclipse, this is something that you might see. You might see these long tendrils coming off the sun. So the sun is behind the moon. The moon is the cratery material that you see here. And then you start to see structure, loops and streams away from the sun. So this is our first clue that the sun isn't just a boring ball, that there's actually something going on, and it's interacting with its environment. It's actually creating its environment that we all live in here. So again, if you went above above the atmosphere, you would see it more clearly as kind of a yellow ball. But you also notice that it has some blemishes. It has these little blemishes. And these are sunspots. So these sunspots are a concentration of magnetic energy. So the magnetic field is especially strong here. And these are the sources of those loops, of the material that's streaming off of there. So these intense magnetic fields are what rule the sun. And in that way, that's something very different from what we experience here on Earth. Most of the things that we experience here on Earth are not controlled by magnetic fields. But as we go closer to the sun, and as we decide we want to go and actually experience its atmosphere, we really have to start thinking about what it's like to live ruled by magnetic fields instead of ruled by the gas in the air or basic mechanics. And this is what the sun looks like from a view from the magnetic field. This is an extreme ultraviolet, so almost X-ray level light coming out, and you see these explosions coming out. You see these bright spots. These are over sunspots. There are many more sunspots during a maximum. The sun has a cycle. It goes through an 11-year cycle. It goes through a maximum where it has many sunspots like this, and then a minimum where it only has 1, 2, maybe 0 at some times. So this is a more active time, and you see things flowing off the sun, things being ejected from the sun down in this corner. So play again. And that explosion right there would power the US power grid for over 180,000 years. So if we could figure out a way to get even some of these small flares back to Earth, we could have a lot of power there. And the mass that it sends off is equivalent to what would be the mass of 80 million school buses coming towards us at 1 million miles an hour. So there's this huge amount of power and gas and just things coming off of the sun. The sun is not just that boring ball. It is this very dynamic place. And we look in these very high temperatures. So this temperature also of this region of the sun, the atmosphere, the corona of the sun, is over 1 million degrees. So this 1 million degree plasma is what we are trying to hope to touch and to understand with Parker Solar Probe by actually putting this probe close in. And now taking a step back, the white circle represents where the sun actually is. And then we took a mechanical finger in a telescope and blocked out the rest of the sun so that we could see that those streams don't end very close in. They actually go off and many other explosions happen. So you'll see very long streams going way off towards Earth. The dots in the background are background stars. And so those are stars outside of our solar system. And so all of these coronal mass ejections, as they're called, are coming off. They go from around 3 to 5 a week in minimum to that a day in maximum. So the whole system, this whole atmosphere as well as environment that the sun builds around it, has a constant change to it. There's constantly injecting energy, constantly throwing off energy towards the Earth, towards Mars, towards everything. So as we become explorers, we really need to understand what's going on so that one of these doesn't affect us. So again, a reason to go to the sun. Again, for scale, here's a picture of the sun. Here's Earth. That's one of those, one of the starts of the coronal mass ejection. So we are very, very small compared to any of these. But why we're going to the sun again is because we are explorers. We live on this planet and we depend a lot on technology. And all of those explosions actually, it can interfere with our technology. It could interfere with power grids and other things. And as we go to Mars, as we go to the moon, as we go and explore the rest of the solar system, we really need to understand the environment or the terrain that we're going into. There's this practical matter of living with a star, and again, that's making sure our power grids are safe, our astronauts are safe, so that they don't get radiation doses as they go out into space. So that's a practical matter. And then scientific curiosity. We've got a great laboratory for all those stars that you see in the sky right here in our own sun. So really understanding some basic physics, some plasma physics as to how this magnetic field actually heated can be done by going to the star. So again, just to let that sink in, approximate size of Earth, quarter of the sun, we're pretty small. So Parker Solar Probe, this has been 60 years in the making. The Simpson Committee report of the Space Sciences Board, the National Academy of Science, in October 1958 suggested that we should go to the sun. It also created NASA. So we were created, or the concept for a Parker Solar Probe was created and is as old as NASA is. So this has really been a long time in the making. And in that committee report, it suggested that we go to each body in the solar system. So we've gone to Mercury with Messenger, we've gone to Venus several times. We live on Earth. Mars, we've explored with robots, we've explored with other telescopes or orbiters. Jupiter, we've done orbiters and flybys, Saturn, Uranus, Neptune, and even Pluto, even though some people don't think it's a planet anymore. We have seen Pluto. But we haven't gone to the sun yet. So again, that committee report stated that these were the goals, to go to all of these bodies, including the sun. And there really wasn't, up until about now, we weren't technologically ready to go. There were initial concepts of we would plunge into the sun. We would try to plunge into the sun and it would be a one-time shot. Well, if you say your instrument didn't turn on that one time, you lost all the data. So you just spend $1 billion and you have no data to show for it. And that's not a good day. So that concept wasn't accepted. Then there were other concepts that the heat shield would eventually disintegrate and dive into the sun. And that didn't seem to work because the technology wasn't there. And finally, at this point in time, we figured out a way to protect ourselves enough that we can orbit around 96% of the way to the sun and be successful. So why this again is important is who has used something like this today to get anywhere? The Google Maps. Anybody use Google Maps today? I know I've used Google Maps today. So GPS, the GPS signal can be disturbed by those solar storms that we saw, and you can be off in directions. And so, you know, that's not so bad if you're walking down the street or even driving. You can kind of correct, but that's really bad for things like autopilot on flying planes. That can be very catastrophic. So we definitely need to make sure that we understand the GPS and it's not messed up by these solar storms. The other thing is any type of electricity or power. Again, if you want power to your power grids, you want to watch some TV, some Netflix, Hulu, whatever you're going to watch. You really need to have your power, and you need to make sure that it's steady and that the power grid is safe. Power grids sometimes have very long runs of cable, and so those long runs of cable with all this excess energy that comes in from the sun will actually induce a current, and so put extra load on it, and basically break it and cause transformers to catch on fire, and these transformers then would need to be replaced. Certain transformers could take up to 6 months to replace. So imagine turning off the lights to New York City and not having power for 6 months. Those are trillions of dollars worth of assets that would be in jeopardy. Now again, we don't have to be fearful. It's not going to necessarily happen tomorrow, but at the same time, it's better to be prepared. There are ways to safe all of these things if we know that they're coming. And so this slide summarizes some of those dangers. That as the sun gives off its flares, these brightenings, as well as those coronal mass ejections, there are these energetic electrons that can do damage to spacecraft. So telecommunications spacecraft, scientific satellites. There's also issues with the GPS, again, signal, which also gives you radiation on flying when you're flying over the poles. Again, we're inducing those currents in the power system. Submarine cables would be affected, as well as pipelines, any oil pipelines. So these are all reasons why we need to better understand the system, understand when the energy is coming in, what we can do about it, and there are ways to kind of prevent this. But you don't want to say, like, brown out New York City when you're only 50% sure that there's going to be a solar flare today. People get upset about things like that. So the space weather drivers, or solar space weather drivers, I've been talking a little bit about these flares. So starting at the sun, we saw the magnetic fields, or the magnetic loops of the sun, and starting in the base and then going out to the solar corona. Then you see the flares, and flares are catastrophic, explosive reorganization of those magnetic fields. So when the magnetic fields bump into each other, they create those large explosions that is enough energy to power the US power grid for 180,000 years, and that's a solar flare. Associated with the largest ones, and sometimes not even associated with any flares, are the coronal mass ejections. Again, all those school buses. And those also create solar energetic particles. So these are the most basic building blocks. The protons, the electrons, positive and negative particles that come streaming out towards the Earth. Could also be towards Mars, could be towards the Moon, could be towards Saturn, any other assets in the influence of the sphere of the sun. That those can also come in, and they come into the sun. This is the Earth. This is the Earth, and we have a protective magnetic field as well. So our magnetic field actually does create a bubble around us, and as long as our bubble is secure, most of these things don't pass through. But if the direction of our magnetic field is actually opposite of the coronal mass ejection magnetic field, you can actually unlock this, and all the particles go streaming in and create aurora. So there's actually a very beautiful result of space weather, but at the same time, you don't want all these particles coming in and, say, damaging your spacecraft or inducing those the currents in the power grid. So beyond that, and beyond really starting to understand all of those the three sources and where they are and kind of how to measure them along the way, we have some scientific curiosity, and that's what's motivating Parker's voyage to the sun. The sun is really mysterious, and it does at least two weird things that we're still trying to figure out as scientists. And the first one has to do with what I call the campfire effect. So as I think we've kind of all experienced a campfire where there's a nice fire raging in the fireplace in the outside of this building, that when you walk away from it, you get colder. You walk towards it, you get warmer. So the sun's main heat source is in the interior, is fusion. And so we're making temperatures there of around 15 million degrees. And you start going out from there and get to the surface of the sun, and you get to a cool 5,800 degrees. Cool, it's cool there. And then as you though go further out, so you go to the atmosphere of the sun, it goes back up to 1 million degrees. So kind of what happened, you walked away from that campfire and you suddenly got warmer. So that's one of the weird things that the sun does. As you get away from its heat source, you get colder initially, but then you get hotter. So we want to understand where that energy generation is coming from. There seems to be a place that's creating energy that's not at the source. So these are some of the mechanisms that we're looking at for the generation of that energy and that heat, and that all comes from magnetic fields. So on the left, you see a video playing of the Solar Dynamics Observatory images of the sun. You'll see there will be some kind of movement, almost tornado-looking movement on the sun of some of this gas that is tangled up in magnetic fields. And on the right, what you'll see is a schematic. These are the magnetic fields, so just a cartoon interpretation of them. The surface of the sun. And underneath there's some circulation pattern trying to kind of move the magnetic fields around. They're anchored, think of them as being kind of anchored and you're moving them around. And by that and creating waves, kind of like these waves, they think that there's some friction and you actually create some heat there. So that would be one way that we think that this campfire effect might work. And then another way is through those solar flares. There we go. So through the solar flare. So again, it's a violent reconfiguration of the magnetic field. So you have one magnetic field that's closed, meaning both ends are locked to the surface of the sun. Again, you have some circulation trying to move the bottoms of them, and some open magnetic fields. And when they collide, they create energy and sending energy both up and down, much like in this flare video over here from, again, NASA's Solar Observatory. So these, again, are images at around 1.5 million degrees. So this is very hot plasma reorganizing itself and putting off heat. Oh. There we go. So one of the things that we observed early on was that these comet tails are always pointing away from the sun. So there's not only this heat that heats this corona to the 1 million degrees that we don't understand, but kind of the other weird thing is that there seems to be a constant outflow of the sun. So it seems like the worst diet ever. You're trying to lose weight, but you never really lose weight, but there's constantly things flowing out. So it's this weird thing that the sun's doing. And so this would be, the sun would be over here, and these are images from stereo that take the solar wind, which is called this constant outflow, out of past the sun and away. And so, but never fear, there are many people studying these two weird things. So these are the scientists that are just some of the scientists that are involved in Parker Solar Probe, and this is actually Eugene Parker, the namesake of the probe. Gene is a model of perseverance and a brilliant scientist. He works at the University of Chicago. I have had the pleasure of meeting him multiple times, and his initial paper in the 1958? I think it's 58 paper, was to theorize that there was this solar wind. And at first, when he turned it in, the review article or the reviewer that he got said that this was nonsense, that this wasn't something that was going to be publishable. But he checked his math and he said, well, but I think the math kind of works out. So he went to the editor, and the editor looked at it and said, well, you're right, the math seems there, so why don't we go ahead and publish it? And so he's someone who persisted and was sure enough in himself that said, yeah, I seem to be onto something. There seems to be something here. Why don't we go ahead and try this? And so he's made a career and is actually the first living person that NASA has ever named a spacecraft after, due to this perseverance and due to his work in this field. So the mission and what we're trying to do is to really go in. We launched on August 12th, 2018. Went in straight past Venus, and Venus gives us an assist. She assists us 7 times and takes some of our energy and pushes us in further towards the sun. And our first closest approach was on November 6th, and that was at 35 solar radii. We've done 2 more at that radius, and we will then step in this January. We dance with Venus again on December 26th of this year, and she pushes us into 29 solar radii, and then we will step in again in July of this year, or July of 2020, and then subsequent years until we get to 9.8 solar radii. So this is, again, a picture of the sun, kind of to scale, and these were all those outflows that we saw. And this is where Parker Solar Probe is going to end up. So to scale, this is what we should be flying through. And I gave this talk, or similar talk, to a 5th grade class. And I told them about, oh, look at all the things we're going to fly through. And one of the little boys said, I bet your spacecraft can't make it. I was like, thanks. Thanks, kid. Thanks, kid. Yeah, thousands of engineers in NASA can't make it. Okay, thanks, kid. But what he doesn't know, and one of the things that the data has already revealed, is we thought that we originally did the calculation that we might see one of these events, one of these coronal mass ejections, in the 7 years of our nominal mission. In our first orbit, we flew through 2 of them. And survived. so haha there. 5th grader. So once we get there, all the way in there, as well as right now, we really wanted to take the temperature, because that's one of the things that we said was a mystery, is why does it get up to that 1,000,000 degrees? We basically also wanted to measure the wind speed and direction. We're going to take our magnetic field measurements, as well as to take pictures, because as every good trip, you always need some good pictures. And this is the spacecraft as designed and as built and flown. So the SWEAP instruments, there are 2 shown here. The SWEAP Solar Probe Cup sticks out. It is the bravest little instrument. It decides that since we were going all the way to the sun, we're going to stick out and actually allow the solar wind to hit us directly. Everything else hides behind this thermal protection shield, which keeps everything actually cold enough that at closest approach we need heaters to keep the electronics warm enough to work. Alternate irony, right? You're at the sun. Why are you cold? You need heaters at the sun. We have this amazing cooling array system as well to wick away the heat that is placed here from the sun, and it's made of water. It's a water coolant system. So kind of the basics. There's a high gain antenna, and that's our phone home. That's how we phone home, and that's how we transmit all the data. We don't get constant data, which is strange for our type of mission. For planetary missions, this is normal. You get kind of certain times where you can talk to it. Solar physicists are spoiled. We're used to low Earth orbit where we could talk to it almost any time. But this one, we have to point this specifically at Earth and make sure it's at the right direction. We also have this SPAN-B instrument, which is an instrument that measures, again, those protons and electrons and actually electrons for SPAN-B. And then our power source are these solar wings, our solar arrays. And our solar arrays actually articulate. They're not just big flappy arms. They have fingertips that pop out, because at closest approach, if we left our solar panels all the way out, we would actually overheat them and fry them. So we have to pull them in, and we only allow their very fingertips that have less lower absorptivity or lower efficiency out, so that you don't burn up, you don't put too much heat on them at closest approach. And if you flip the spacecraft over, the field's antennas measure magnetic fields, or the magnetometers back here, magnetic fields and electric fields. There is the SWEAP, the third part of SWEAP is SPAN-A, which is protons plus electron measurements. The ESIS suite, which measures all those solar energetic particles that come off of the sun, and it looks like a little mushroom detector. And then the field's magnetometers are back there. So this is me and the spacecraft. This was after about 14 hours, and if you see on top, we were actually doing a magnetic swing test to make sure that we could measure those the magnetic fields very sensitively. We had to make sure the rest of the spacecraft had no magnetic fields left in it, so we were actually just measuring the sun's magnetic field. So we had to lift it up and actually swing it back and forth to actually make these magnetic measurements. So it was a long day in the clean room that day. But another picture to just orient Solar Probe Cup looks directly into the sun. SPAN-A are over here, and then these are over here, and the SWEM, which is our brains, are inside. And these are our actual baby pictures when she was ready in actually Goddard Space Flight Center doing some testing. So you put them in this room, and there's actually a large speaker where they shake the spacecraft. So they play frequencies and they shake it to make sure that it's going to survive that launch vibrations. So she was all ready for her launch test. But this is the Solar Probe Cup. This is a blow up of the span B. Particles come in here and are chased around here into this electronics box and analyzed. And then this is a 2-hemisphere detector as well as span A. So what's our role, the SWEAP suite that Ben and I are a part of on Parker Solar Probe? So again, we're measuring the electrons, alphas, which are helium atoms that are stripped of their electrons, and protons. And that's the bulk of the solar wind. So that's most of what's in the corona, most of what's coming out, and that's what we're measuring. And we do that so that we can actually understand where the energy is, because it's basically a deal. There's only so much energy, so what's carrying it? Are the protons carrying it? Are the electrons carrying it? Is helium carrying it? Who has the most energy, and where are they going? Because that gives you clues as to how things are heated, whether it's the heavy things like protons and helium that's getting the heat, or whether it's the lighter things like electrons that are carrying it. That'll tell you a little something about where that heating is coming from. And to determine the structure and the dynamics of the plasma and the magnetic fields in the sources of the solar wind. So again, figuring out where that solar wind is going, and then exploring things that, how do you accelerate these energetic particles? This bulk of the solar wind, not all of it will be accelerated, but some of it could be accelerated to high energy particles. So how do we understand that? And that's what our role is to measure. And this is the cup. This is the Faraday Cup. It's a cup that has a lot of heritage. It was flown on things like Voyager. It's flown on Wind. It's flown on the Discover spacecraft. So there's many other spacecrafts. But this one was a little special because this one, again, is the one that we decided to stick outside of the heat shield. So it has its own heat shield. It has sapphire in terms of some of the material, some of the insulator. Normal insulators would be something like rubber. Rubber melts at temperatures of 1800 or 1400 degrees, so we couldn't put that in there. There is different alloys of molybdenum, tungsten, as well as TZM out here in order to make sure that it doesn't melt. And then you get back to the electronics box where it's going to be much cooler. You can get a little closer to your normal titaniums and aluminums that you would use in spacecraft flight. So this was really something that is completely handmade. I'm not sure if you can see, but they another thing that we normally do for those shake tests is actually glue screws down so that they don't fall out. You couldn't use glue on this because it would melt. So instead, every one of these knot screws, or even double knot screws, had to be hand tied with wire so that they wouldn't fall out. It is just an absolutely beautiful work of art for a scientist and for an engineer to look at in terms of how much planning had to go into every single bit of this so that I could survive the 1400 degrees and so that I could survive launch loads that would shake most things just to absolute pieces. So how we do our orbital operations was that our prime mission is within 54 solar radius of that. So about 75%, we get 75% of the way to the sun, and that's when our operations started. So that's where we take all of our data. And then outside of that, we go ahead and we start downloading some data or taking some data and alternating that, because again, the spacecraft has to turn to call home, and that makes it busy, and so sometimes we don't take data out here, and then we get ready, and then we go back in and we do that. Now that was the original plan, and we were only supposed to get 20 gigabits per orbit, so yesterday I was supposed to serve 40 gigabits because we had 2 orbits worth of data. We ended up serving, I think, over 80. So we've gotten much better downlink, and it's just been amazing. It's been 4 to 5 times the amount of data that we thought we were going to get. So this mission is already doing just amazing work. And so we don't take pictures again. The SWEAP suite has the squiggly line plots, which we'll go through in a second. But there is an imager, the Whisper imager on board. And this was one of the images where the sun is over here and you're seeing the outflow. You're also seeing Mercury. I put this in because there was a Mercury transit yesterday where the Mercury went across the sun. You can see it in the SDO images as it transited the sun. And this right here is just a picture of Mercury. These dots are actually a background subtraction, but that is actually Mercury that we've taken a picture of. And we'll be encountering Venus, and in the third Venus encounter, Whisper will also be taking pictures of Venus. So we've not just got the science of the sun that we have, but we've also now started to do some planetary studies at Venus. Our first flyby, we took data there, and the planetary community is very excited that they get 6 more tries, that we get to turn on these plasma instruments and actually do this. Now, it might not seem like this to most people, but NASA kind of has some departments. You have the Planetary Science Department, you have the Astro Department, you have the Earth, and you have Helio. And normally you don't kind of go across those boundaries. Whereas now with Parker Solar Probe, it's not only doing its own science, but it says, hey, we would love to collaborate with you guys. Like, we'll do some planetary science. There's also been the request of doing some astrophysics. So this is really this mission that was so focused on the sun, but it's actually able to do other things as well. So it's just a great mission. So August 30th, 2018 was actually our first light from that Faraday Cup. So what you're seeing here is the time across the bottom, and this is about minute steps. And then you're seeing the speed. So you're seeing how fast protons, just protons, because we turned the electronics to only measure positive things. So proton speed in kilometers per second, and that the base where this gets most intense is around 400 kilometers per second. So as we were measuring, we found that most of the particles that we measured were around 400 kilometers per second. So this is going extremely fast. Well, fast for us. Solar wind can get up to around 800 degrees. So it's kind of a mid-range, mid-speed wind, which is amazing. And we did not think that we would see it this far away from the sun. This whole instrument was designed to be very close to the sun, to have when we have very high densities, and kind of optimized for that. But because we happened to just turn in the right direction and we're able to see this, we were actually able to make these measurements all the way out at around 0.88, so very close to the Earth instead of very close to the sun. And so it's not just the SPC that we have as part of the SWEAP, but we have the SPAN ions. And when their first light on September 8th is we actually had to turn the spacecraft in order to get the solar wind to turn into our instrument. And so when we turned, because the wind has a directionality into it, we did see, this is again in 10-minute increments, every time you see something that's not this dark blue, we're actually getting particle counts. So we're getting particle counts and saying, oh, this is how many counts we have, and this is when they started and stopped, which means if you get both of them, that actually tells you a little bit of time of flight. That will tell you a little bit about the composition of the ions that we have there. And so we really have had just amazing measurements. We've made more than 1.8 million samples of the solar wind that were recorded and downloaded in just one orbit. So we've now had 3 orbits. And so we've recorded, I think, around 5 million spectra, something like that. So to compare this to, say, the WIND spacecraft, which has been up for 20 years, we've taken about 5 years of that data in less than, in about 6 months. So we've really taken a lot of data. So this is just showing you the time between the spectra versus the day of year in 2018. And so this is, how many spectra we are taking, and we're just taking tons and tons of spectra all the time and constantly going through and making sure to make it right and to make sure that this is something that is interesting for all the scientists. And so that's what yesterday was about releasing all of this data to the scientists and having them have at it. Because this isn't just something that's for our team, but it's actually for the entire scientific community. And we also, so this mission is the closest, it is already the closest human-made object to the sun. It broke Helios's record as of October 31st. It's the fastest human-made object that was also broken around October 31st, actually November 6th, I think. And it has done the fastest measurements of the solar wind. So these are measurements from SWEAP, from SPC, and it gives you the total current, or basically the total counts. Just think of that as counts. How many of these things are you getting? It did 300 samples per second, which is equivalent to being able to sample something at 1 kilometer. So it's like taking like a map and being able to, at every 1 kilometer in the sun, actually making a measurement there. And these are flow angles, so it's telling you how the wind is actually flowing into the cup. And those were measured at 300 samples per second. So this is a very the fastest measurements that have ever been made of the solar wind. And so, again, I told you we do squiggly line plots, and here's kind of the basis of the squiggly line plots and how we start with this. How I would think about it is like, how frequently do we measure this? And then what velocity are we measuring? So these are 3 different samples that we've taken, and we say, okay, I step through things, and how I measure things is saying, okay, this is 300 kilometers per second is what I measure most of the protons at, the H+, the protons at. And I've measured them how frequently? Oh, I measured about this much of the time. I measure this less time, and I measure helium this less time. So this is what we do to build up. And we pick these peaks as a way to then say, okay, the solar wind was at 300 kilometers per second. That was that measurement at that point in time. And then it kind of moves based on timing. And then you kind of get confused sometimes because the solar wind's doing multiple things. Again, that trading of energy, that figuring out of who has all the energy, playing who has all the energy. Is it the helium? Is it the protons? Or is it the electrons? Because we also do electron measurements. So this is what the scientists look at and get really excited about and spend lots and lots of time doing. But then we also do things like this, where we try to make it a little bit more kind of generalized so that you understand this is time on the bottom. These are the 15 days around closest approach. And as we went in and then come out of approach, this is the speed, and it's the 3 components of speed. So we have vector speeds in the radial direction, tangential, and normal to normal speeds. We have thermal speeds, which are your temperatures and how the temperatures increase and decrease. And then we also have density. So we've done the density, temperature, and speed of all of these things. So this is again telling us, is there a coronal mass ejection? Because that would be an increase in density, possibly an increase in speed. And so we look for things like that. And I can point out here that there was a coronal mass ejection here. This was a coronal mass ejection. And then 11th, it's actually over here. It's not plotted on this one. The second coronal mass ejection from the first orbit. So again, to you, it looks like squiggly lines. To me, it's two coronal mass ejections, which I very much stared at a lot, plus a lot of other data, because this looks very busy and very squiggly, and these are 15 days of measurements. But if you zoom in, you see that there's all this detail. This is only 15 minutes. So we've gone from 15 days to 15 minutes, and there is just so much resolution, because again, these have been the fastest measurements that we've really ever made. And this is around closest approach, and what we're plotting here is the velocity, and then the magnetic field. Then we have the changes in them. So how do they change I think it's R and T, radial velocity, tangential, and normal. And we're seeing that they actually are kind of following each other. And these are very interesting and hinting at a very interesting scientific result. And those scientific results will be out on December 4th in some Nature papers. And so just to show some other things, some electron measurements, because we also have done electron measurements with this to, again, understand, do the electrons hold all the power? Are they the ones that are really involved in this heating mechanism? The top measurement is magnetic fields. This is, again, the entire first encounter from October 26th out to November 20th. And here you can see, again, coronal mass ejection, coronal mass ejection. It's one of those things like only a mother can know them, like, oh, I know exactly where my 2 kids are. Here's my 2 coronal mass ejections. And things that you see in, let's look at the normalized pitch angle. So these are where the electrons are coming from. You'll see around them that they end up coming from both directions. You'll see a bright here and a bright here, and then there should be bright here and bright here, which means that there's actually loops that are connected. So either they're connected like this, and you have electrons coming this way, and you have electrons coming this way, or you are connected back to the sun, where electrons are coming back here and then going back that way. So that's what pitch angle distributions or electron measurements can give you, is to tell you which way the electrons are flowing. And that tells you if you're still connected to the sun, or if you're connected to a loop that's broken off and that's formed its own little circular wedge that comes out at you. And so those are the types of things that we look at and that we will be studying to really understand how all of this heating works. And so this takes many scientists lots of time in order to calibrate this. Also looking at things like density. Again, density increases during, actually falls off during, increases over the coronal mass ejection, and temperature dropouts as well over there. So overall, the instruments that we have on this are performing extremely well. And we're already seeing some really stunning new results in the first and second encounter. And we even have data from the third encounter. And that's really been just a testament to the thousands, and it is thousands of people who have worked on the spacecraft. So there are 4 instrument teams and probably around 100 people on each of those. Then there were engineering teams. And actually just yesterday, this project was awarded NASA's silver medal for group achievement. And there were thousands of people there listed in order to make everything from this heat shield that keeps us, again, cold enough that we need heaters at closest approach, to all of the instrument scientists that built the Faraday cups, the electrostatic analyzers, the magnetic field sensors, the particle detectors, all of those people. It took thousands of people in order to do this. And we released the data yesterday at noon. And it's being downloaded, and papers are definitely being written. The teams have had the data for about a year, and again, it's been a year of calibration and really getting them into file formats that everyone else can use. And we've submitted 60 papers so far to the Astrophysical Journal, and those should be out in February. And we expect that many, many more will come out in the coming months. And for Nature papers, there are 4 Nature papers that have been accepted, and that will be out on December 4th. And so there will be a press release that day on these 4 changing things. And what you should probably look for is that this might have something to do with that. I can't say a lot, but it's something. So that's something that will be coming out later. And so with that, I want to thank you for your attention. And this is actually the SWEAP in Fields. As I was talking about all those people, this is just, again, 2 of the teams before launch in August 2018, and all of our families that support us and all of our friends that were there to support us to do this. And continue to follow our adventure. We're on Twitter and Instagram at The SWEAP Life. And thank you again for all your attention. And I'm more than happy to do questions.
Thank you so much, Kelly, for that excellent talk. Let's open it up to questions. We have 2 people with microphones, 1 in either aisle. So if you have a question, please raise your hand and wait for someone with a microphone to come to you so that everyone can hear your question. And I see a question up in the front here.
So, I told a friend of mine about this right before, you started giving your lecture, and I was wondering, I've noticed a couple of cameras around. Will this be Was this recorded? Will this be available to watch, or this slides available?
I think so. Should be. Oh, sorry.
Yes, it will be video. It is being videoed, and it will be available probably in about a month. If you Google the lecture title, it should come up.
From a construction and engineering standpoint, how do you harden the craft against induced current, keep the instruments from being fried by the magnetosphere?
That's yes, that's very good. So spacecraft charging is definitely needed to a consideration. So part of it is making sure everything's grounding. There are ground paths to everything. We shield. So there's the induced current of flying through a plasma, but there's also then the possibility of radiation basically coming in, those energetic particles, and that's done by thickening up things like putting in a couple thicker aluminum sides so that they actually can't get through and can't break down the electronics. So you make sure you have all your ground paths. You make sure that there's a way that you can basically, we do not actively discharge anything. It's statically discharged. And so that is a concern. We do measure and worry about spacecraft charging. However, our electronics have their ground paths, so they should all be fine. And then the energetic particles we protect against by shielding. So having slightly thicker boxes. Other questions?
What kind of material is the thermal heat shield made out of?
It's similar to the tiles on the space shuttle, so it's a carbon composite, and then there's a layer of felt as well, a carbon felt that's there, so that dissipates the heat enough that it does not burn up.
So the layers of felt underneath it, is that acts like as a heat sink?
Yeah, the whole carbon, all the carbon is a great big heat sink, and it just basically takes it and then dissipates it out towards the side. So you focus the sun on the top, and then it allows the heat to go out to the sides as well as back into the cooling system, the water cooling system, which then takes the rest of the heat out of it.
Oh, okay, thanks.
How well understood is the 11-year solar cycle that you spoke of, and will this probe provide ways to understand it better?
Great question. So the 11-year cycle is pretty well understood, but saying that, our predictions are always kind of off. Is it 11 and a half years sometimes, 12 years? So we understand the basic mechanism, but still the exact timing is not well understood. So what this probe will do is it will focus on the magnetic field and measuring it close to the sun. So that will help us kind of understand what the magnetic features and how it changes. We have at least a 7-year mission, which will mean we'll sample parts of it from when it's at minimum to when it's at maximum. So we'll get samples all along that, and then we will have to combine that with data on the ground from things, anything from the Solar Dynamics Observatory makes measurements that will help with this. A DKIST is coming in line, a telescope in Hawaii will come online that will also help with these questions. So really it's going to need to synthesize several things in order to better understand the solar cycle.
What was the one wow moment or thing that you didn't expect to find that you did find?
So many things. So definitely the 2 coronal mass ejections was not something that we expected to see. These coronal mass ejections, as you saw in the Solar Dynamics Observatory images, are really obvious, right? There's big explosions coming off the sun. But there's this class of stealth CMEs that you can't see, but that you sometimes experience at Earth. And so to see those 2 that, again, there's not a lot of evidence from Earth, but we see them there. That was a big wow moment. And then I think, engineering-wise, the biggest wow moment was actually that picture was of me with the spacecraft. Was one of my wow moments, standing there, and I was a little crabby because it was a long day and I really just wanted to go to dinner. And the person who was standing with me told me, look at that spacecraft. That spacecraft is going to go, you are standing 2 feet from a spacecraft that's going to be 96% of the way from the sun. It's like, okay, I'm not so crabby right now. Like, okay, this is awesome. I still want food. It's really awesome. So that was my other wow moment.
I was just curious about, at the other edge of space, what does the heliosphere do? What is its impact way out, like at Neptune or Pluto? And then what is what happens when there isn't one? What difference does it make, in a sense, when I think it was some spacecraft just went through it and now is out in open space? What difference does that make?
Right, yeah, so that's a good question. So this protective bubble that we have, I kind of always focus on the front part, to the front that the sun is kind of pushing through the galaxy in, because that's kind of closer to the sun. But Voyagers have just gone outside of those and have just said that you're now touching the outside. So you're touching interstellar space. You're touching the space of the galaxy, the space in between other stars. And so it's a change because you don't have that protective magnetic shield. Cosmic rays from all over can kind of come in. You're not really under the sun's influence at that point in time. You're in interstellar space, and so for Neptune, it's still in the protective bubble, but as you go further and further out, you can imagine that the effects weaken, so that protection weakens. So you can get more energetic particles in. You can kind of, but at the same time, you really don't sense, because there is a kind of a shock or a boundary between that. But eventually, it will taper off, and you will leave and go outside of that. And there are missions in the works to actually go and visit that, to go and understand it better as to how we transition outside of our safe solar system.
Oh, is it I? Sorry. When you're taking that many measurements per second, how do you have enough people? How do you have enough time to read all those measurements? Do you have some way of condensing?
Right, so that's exactly, so there is a lot of computer work involved, right? And so there is a lot of processing that you put on flags and say, okay, basically there's a general way to fit everything, let's fit it, and then see when there's large errors on it. And when there are large errors, then you can go in and investigate and see, and Ben has worked on this, and as well as a bunch of our team of 80 people have kind of looked at that and been like, why is that not a good fit, or why is that not a good measurement? And to try to do that. And even with those people, it's going to probably take the 60 years, 70 years, in the future, that people are going to have to look at this all over the world and really say, okay, was that a real measurement, or what that was, in order to really truly understand everything. So it's amazing that we have all these data, and they're going to be around for a long time. So it's a good thing. We're just going to need people eyes on them for many years to come. We did a really great effort and got probably like 70 to 80% of the way there, and then we're going to need everyone to look at it to get the rest of the way.
What would happen if a solar flare hit the Earth?
Oh, if a solar flare hit the Earth. So that would be, the solar flare itself should hopefully stay within, kind of within the sun, closer to the sun. But what's going to happen from that solar flare is that energy is going to come off towards the Earth. And again, if it'll direct its energetic particles towards the Earth. They'll come in, and they'll come into our magnetic field, and they'll make aurora. That's the best thing that can happen. So we'll see these gorgeous greens and reds in the sky. It's exciting the oxygen and the nitrogen in the air, and it makes these beautiful colors. And if you ever get a chance to see one, definitely go outside and see one. They're beautiful. They're absolutely gorgeous. And that's kind of one of the good things that could happen. And some of the bad things that could happen are things like the satellites, their electronics won't work anymore. And so that's a problem. And something about like GPS won't work. So you wouldn't be able to drive use Google Maps and things like that. So those are things that would happen if the flare actually hit the Earth.
This will be my last one. I want to give room to others, but being that you've surpassed, I think it was Henry or Henrik, that was the previous one that was getting closer to the sun.
Helios, yeah.
Being that you're so close to the sun, are there hopes or any plans for, say, maybe getting closer to the sun's surface or onto it and scooping up material?
We would love to, but there's no plans. It does get to the point where part of why we're able to survive the heat is that we go in fast and we come out. Because we're used to conduction, where you touch something and it's hot, and that's how we transfer heat, and then you get hot really fast. And so if you were to scoop up the sun, that's what would happen. We're much more than like touching a hot stove. We're kind of in a sauna. So in a sauna, you can kind of, because it's less dense and because there's not the conduction hitting your skin of all the air molecules, it's a lot less, there's a lot less transfer of heat. So we're able to go in fast and not transfer all the heat because we don't stay too long and then come back out. So there's no plans, but you know, NASA's always looking for good proposals. So if you have any proposals, anybody? Other questions?
Thank you. I'm presuming that the orbit of the spacecraft is in the same plane as the planets. Do you have any control of that in terms of altering how it approaches the sun?
So the most energetically efficient way to go is to stay basically stay as much in the plane as the Earth as possible. Every time you try to deviate from that and go away from the plane, that's extra energy that you have to either push yourself up. And so our sister spacecraft, actually Solar Orbiter, the European mission to the sun, will launch in February of next year, and she will join us. And their focus is not to go in as close as we do, but to actually go up at an angle. So they'll go up at about a 20-degree angle, and that's a little bit about trajectory, a little bit about how you launch, as well as then a little bit of maneuvers to get themselves out of the ecliptic. We're going to stay in that plane with the Sun Earth as close as possible, and how we spiral in is with Venus assist. And so Venus gets a little of our energy, takes it from us, and pushes us in further each time.
Which you wouldn't have the option for in a polar type.
No, you wouldn't have you couldn't use Venus at that point in time. You can do some type of slingshot over Jupiter, but that's JPL can tell you much more about that. Yeah.
That's a long haul out and in again.
Yes, exactly. And that was one of the beauties of this mission, is that we started operating within a few months, and that's really key to getting the science data out. When you have to go all the way to Jupiter and then back, there's normally a long cruise phase, and then that just lengthens the length of the mission. Yeah.
Will that distribution of particles that you measure, the types of energetic particles, affect what you find, affect the ultimate fate of the sun, or how it's likely to die in the end?
Yes, so the sun will eventually kind of puff up, go into a red giant, and then kind of collapse back down into itself. So we will, how it gives off energy will affect kind of how long it lasts, but it's still something like 5 billion years. So it's 5 billion years plus or minus a couple million is not. It's kind of in the noise right now.
Seems to me I heard that the spacecraft has an unusually high velocity. Is there a reason for that? First of all, is it right? And is it all right?
Yes, it does have a very high velocity, and that's again the trajectory to go in and to come out. We have to go that fast when we're closer to the sun, and then come back out, and we kind of slow down and then go back in very quickly. Yep, we are very fast.
Could you expand on that a little bit, because the mass of the sun is so great?
Yes.
And you're getting that close to the sun.
Right.
How does that affect what you decided as far as velocity?
So in some ways, I don't know if we've we are kind of not locked, I wouldn't say locked into, but because we chose to do the Venus gravity assists, and this is probably actually the part that I'm weakest on. There's a brilliant woman at APL who actually has done all these calculations. As you go in, you have to kind of exchange energy, and in order to turn so quickly, you need to keep that energy up so that you get back out. And so that's what you keep doing, and you use the gravity assist then to change you into the direction going back in closer and closer to the sun. So that's a tough one, but I can give you a contact later as to who to really talk to about that one. Questions?
Thank you. It was a fabulous lecture.
Thanks.
I'm wondering, managing all these scientists, your introduction talked about your management skills. Do you have any words of wisdom or anything you've learned about how you manage a team like this, the project like this?
Actually, yeah. So one of my other things that I do in my life is I am studying to be a yoga teacher. And so part of this is bringing mindfulness and the human connection to science. Because I think that maybe the media, and maybe just even probably when I started, I thought that scientists were kind of robots, like a Data from Star Trek, is that I'm just using all of my facts, and I'm going to use all my facts, and I'm going to build this thing, and it will be fine. I'll do the numbers, and it will all work out. But it really is about the humans. It's about human connections. It's about understanding humans' motivation, understanding why people do things, understanding how to keep a team motivated, and also allowing their human needs to be met. I mean, people need vacation, people need snacks, people need a nap, people need all of that, and to keep that in mind while you're doing the science. And you're going to get the best results if you have people who know that they're heard and that they're seen, and that they really matter, that everyone on the team really does matter, and how do you show that to them? So trying to find ways, and it's different for each person. One person, some of the engineers I work with, if I were to tell them how important they are, they would flip out. They would be like, you're telling me, and I'm like, well, you're really important to this. Don't tell me about your feelings type of thing. They would never want to talk to me again. So I need to be able to, reward them in different ways than I reward someone else who needs to hear that, no, you're very valuable and I really value you and thank you. You need to figure out all those things. So those are the things that kind of I learned along the way of the last decade of working with this team.
Any help for the fusion energy project?
Sorry, I didn't understand the question.
The fusion energy that, like we have the fission reactors.
Oh,
so the fusion reactor.
Oh, yeah, no, I don't have any insight into that. Yeah, we should work on that. Someone should work on that. Any other questions?
Oh, I think there's one more question over here.
How do you measure the temperature of the sun without melting everything that tries to get close?
Close to it. Okay, so we know the surface temperature comes from basically kind of a theoretical calculation, observations and theoretical calculations as to how much heat is emitted based on the temperature. We can do that. Then how do we measure everything else? So a lot of these things have been done remotely. You do it with spectrographs on the Earth or in low Earth orbit. Those types of things you can measure from far away. Now again, from us, what we do is we use that cup and we take a statistical average as to how many times or how fast things are moving, and that tells you how hot it is. So temperature gets a little weird when you get that hot, that it's about how fast the particles in it are moving. It's not kind of the normal temperature where you take a temperature like in your ear or something like that. That's like, it's a conduction. It's how fast everything is moving. So that's how we take our temperatures there and not melt it. Use very weird metals as well. So.
I understand a lot of spacecraft are now getting an audio channel. Any chance that you have any audio on this unit?
We don't have any audio. We missed a chance there, I think, definitely. But this was, we were very mass constrained, so we do not have an audio channel on this. We do have the downlink, and I'm trying to think of anything that's even close. One of the things that I do, you can watch it downlink when it's downlinking on Deep Space Network, their website, so NASA's Deep Space Network. If you Google it, they will show you which spacecraft they're talking to and which dish on the Earth is talking to it, so you can see the little squiggles that go up and down and tell you whether they're downlinking or uplinking to each satellite. So that's kind of our closest thing to some type of, it's not really audio, but at least it's some type of signal that we're communicating.
Oh, one more question.
You talk about the surface of the sun, but what is that? Is it a mixture of gases that are so deep, so many miles deep, or is it something else? I just don't really know what that is.
Yep. So it is a mixture of gases, just much more dense. So it's a much more dense layer. It's a mixture of the protons and electrons. There's a little bit of things like carbon and oxygen and iron in there, just very little. But it's much more dense. So it's much more like what we're used to in terms of something that's almost a solid versus the gas in the air, which is what would be closer to what the corona would be like.
Getting off to the side a little bit, going back to the velocities, have you had any inquiries from the relativistic people looking to investigate frame dragging?
The only thing that we've done in terms of relativity, I know we do have a relativistic correction to our clocks. Our clocks do need to be corrected for relativity to flying that close to the sun. But past that, no, we haven't been. But again, I'm sure there are people who will use our clock differences that will, things that I haven't thought of yet. And that's amazing.
Yeah, kind of a follow-on to that prior question about the surface, and you mentioned several other elements, and I've always thought of all suns in the universe as basically fusion engines that are just forming the whole spectrum of that chemical table that we are all familiar with from high school. This is ongoing right now in our present sun to be expelled when it explodes eventually, as I understand it. I'm not all how you get from a red dwarf or down and then have it explode. But do we have any idea how much longer after you get to that death stage, Earth is long gone, as when this expulsion will occur, if it occurs at all, giving other elements back out to the universe?
Right. So, so our star is a wimpy star. She's a dwarf. She is not going to explode supernova. She would need to be 20% more massive in order to go supernova. So she won't explode, as you sometimes see in other exploding stars, heavier stars. And that's actually also, she won't go past. She won't really create anything past nickel. You got to go to a supernova explosion to get the nickel and the iron and the things that are really heavy. Our star just can't fuse that, and stars are this size just can't fuse that together because it takes a lot of energy to push things together and add a proton until you get up to those. So carbon and oxygen is about the extent where we get, and then you need to go supernova to have even hotter and higher pressures to make those things happen. So in terms of that, it's a good question as to how the stuff that's left in the sun will be kind of dissipated slowly, kind of outward. That's a good question. I should talk to someone. I'm sure someone in the audience might know this question as to how that, because I'm used to the explosions pushing things out, and that's kind of obvious, but not how when you kind of collapse into yourself, how do you spread out later? That's a good question. I'll have to look that up. Thanks.
Do you remember a moment as a small child when you looked at the sun and thought, maybe I'm going to study that someday?
What's funny is my oldest memory is of the sun. I'm about 2. I'm on the beach in Cape Cod, and I have my little hoodie on, and I'm doing my little sand pail thing. And my dad asks, "Do you want to go in?" And I look up and I just see the sun, and I say, "Nope," and just keep playing. He's like, "You want to keep playing?" I'm like, "Yes." I'm like, "I'm in the sunshine. I'm fine. Like, I don't know what you're talking about. Why go in?" So that's kind of my earliest memories of the sun. And past that, how I got here to the sun is I was a physicist. I took a year off because after undergrad didn't kind of understand exactly what I wanted. There was everything from med school to business school on the table. And I was studying one night, and I went back for a master's degree, was studying one night, and one of my friends said, "Do you want to go watch a video?" And I was like, "Yeah, I want to procrastinate for my homework." And this was in the time when DVDs you had to have a DVD player, and we had to go to a special room in the college to actually see the DVD. So we popped in the DVD, and she showed me the images of the TRACE satellite. And I was amazed at all these, this seething, this coronal mass ejections, all these things. These were amazing. And I was like, okay, well, how do I get into this? And she's like, it's all free. NASA provides all this data for free, and you can work with another professor. And so I switched that month to study the sun, all because I did not want to do my homework. So I decided to study the sun instead.
And I'd encourage my Physics 207 students to disregard that statement.
I'll show you some videos of the sun later.
If there aren't any other questions, let's thank Kelly once again.
Thank you.